Alright guys, this is going to be our last integration by parts video. We're going to start off with a definite integral and we're going to see where that leads us. We are going to run into a challenging problem today, but I think you're going to really appreciate the results. So, here is the first definite integral that we are going to do. We want to find the definite integral from 0 to pi over 2 of the cosine squared of x dx. So, let's think about integration by parts. Get it set up here. And now I want to think about how this should work. So I see a cosine squared of x and I see the dx. Obviously the dx goes there. But how about that cosine squared? If I put it here, I need to take the derivative of cosine squared, which would require me to use the chain rule, because really we've got the cosine of x, in parentheses, squared. So that would involve the chain rule, and I don't really like that. Now, over here, if I put it there, I need to know what the antiderivative of cosine squared is, and that's kind of what we're trying to figure out. We don't know what the antiderivative of cosine squared is. So I don't really like cosine squared in either spot. But then I can think about it and I can say, well, cosine squared is really cosine times cosine. So what if I put one of the cosines there and the other one there? Remember, we have the integral of u dv. So if I take u times dv, that's equal to the cosine squared. So this is worth exploring. So, alright, derivative of the cosine, negative sine. Antiderivative of cosine, sine. I need a dx there. Almost always forget those. Okay, so let's get this going. This is equal to, I'll start with the original here, 0 pi over 2 cosine squared of x dx. Alright, u times v, sine of x cosine of x, I like that, minus the integral of v du. Now notice this is negative sine squared, sine times sine. Alright, how do I feel about that? Might feel like we didn't get anywhere, because now we have a sine squared instead of a cosine squared. So, but then it makes me think like, okay, well, if doing integration by parts once took me from cosine squared to sine squared, if I do it again, might it take me from sine squared back to cosine squared to the original, which we've seen pay off before. So, let's do it again. Let's just go like that, bring that negative out front, and let's set it up again. This time we're going to let u equal the sine of x. We're going to let dv equal the sine of x dx. See if something similar happens here. Du equals the cosine of x. V equals the negative cosine of x. Notice v times du is going to be negative cosine squared, and I like that. So, we have the integral from pi over 2 cosine squared of x dx equals, you know what? I got to evaluate that from 0 to pi over 2. Let's do that quickly. Sine of pi over 2, that's 0, that's term's gone, minus sine of pi over 2, cosine, sine of 0, cosine of 0. I'm botching this all up. Let's try this one more time. Sine of pi over 2, 1. Cosine of pi over 2, 0, that term's gone, minus sine of 0, that term's gone. This whole thing right there is 0. So then we have plus. Now we're doing integration by parts for this part. U times v, negative sine, cosine, minus the integral of v du, negative cosine squared. And let me just make this a plus. Now there we need to integrate from 0 to pi over 2. Okay, and that looks good. Alright, so what happened last time when we did this? We just combined our like terms. I've got an integral of a cosine squared there. I've got an integral of a cosine squared there. So I'm going to subtract the integral from 0 to pi over 2 of the cosine squared of dx, cosine squared of x dx. Apologize for my miswritings there. And let's subtract the same thing over here. This is what we did before. We combine the like terms. However, I realize a major issue. That makes this 0 equals, and if I do my substitution there, I get 0. Oh no! Yikes! This isn't good, right? That doesn't end up getting us anywhere. So that repeating process didn't work out because when we combined the like terms, there was 0 of them. It worked out really well before when this one over here was a minus, and we could add it over, and then we'd get 2 of them. So that's not good. Let's back up. My second integration by parts was not helpful. Again, I really liked when there was a minus integral of cosine squared because when I add it over, I get 2 instead of 0. So here's where we're going to look. Sine squared. Cosine squared. Is there a relationship? You better believe there's a relationship. You guys know what that is. That's 0. This is the integral from 0 to pi over 2 of, what do we know about sine squared and cosine squared? Pythagorean theorem. Sine squared is 1 minus the cosine squared. So now I have a difference. I'm taking the integral of a difference, so I can just split this up into 2 separate integrals. Now I can see when I add this over, I'm going to have 2 of them and they don't go away. Okay? Let's see here. Let's add this onto a new page. Some of my zeros are going to get cut off there, but we'll be okay. Alright, so let's add the integral from 0 to pi over 2, the cosine squared, to both sides. That gives me 2 integrals from 0 to pi over 2 cosine squared of x dx equals, now I just have this over here. What's the antiderivative of 1? With respect to x is just x. So we have 2 integral from 0 to pi over 2 cosine squared of x dx equals, do my substitution, that's pi over 2 minus 0, which is just pi over 2. Divide each side by 2. The definite integral from 0 to pi over 2 of the cosine squared of x dx equals pi over 4. Very good. Alright, now what I want you guys to consider here, if we go back and look at, I guess this one's not really going to be helpful. I want you to look back at this example that we did in a previous video. We started off with an x squared sine of 4x. We did integration by parts. It reduced down to just an x. Now it was cosine of 4x. We did it again and the x was reduced just out of there, down to a 1. And we're back to sine. So we wonder if we can take this and we can apply it to formulas, to developing formulas that we call reduction formulas. So if I want to take the integral of the sine to the nth power of x dx, have we seen a pattern, or could we develop something that can reduce the power of that sine function? And the answer to that is yes. So how are we going to do that? Now remember on this cosine squared, so I'm going to use this to help us a little bit. I took the cosine squared and I split it up into cosine times cosine. Well, now we have a sine to the n. Now if I split it to the sine and the sine, that would be a sine squared, but we need... Sorry, I got interrupted by an announcement on the intercom there. Alright, now that's only a sine squared, but we need a sine to the nth power. Now, I don't want any more than one sign here because the antiderivative of that's not going to be nice. I'm just going to take the antiderivative of that as is, negative cosine. So, if I need n cosines, sine to the nth, if I'm putting one of them there, how many are left over here? The answer to that is n minus 1. So now I need to take the derivative of this, and actually I need a little bit more room because I realize that this is the sine of x to the n minus 1, which is going to require the chain rule. So I'm going to do the derivative of the outside at the inside. N minus 1 sine of x to the n minus 2 times the derivative of the inside is cosine. So, don't forget my dx. There we go. Now, that's kind of messy, but let's see what happens.
Attention all set.
Sorry about that, a second interruption here. All right, let's get this thing set up. The integral of the sine to the nth of x dx.
Just don't.
Well, that was the third announcement in the last minute, but that was for cupcakes. So, I had to go get one. Now, where were we? Setting up integration by parts here. So, we've got u times v. All right, so negative cosine of x, sine to the n minus 1 of x, u times v, yep, minus the integral of v du, negative cosine times all of this. All right, so where do we go with that? Wish that looked more like an n and less like a u. Okay, so we have the integral of the sine to the nth power of x dx equals negative cosine of x sine to the n minus 1 of x. I'm going to take that out and write that as a plus. Now, let's look at what we have in here. You know what? I can also take out that n minus 1. Let's squeeze that in here. Plus n minus 1 times the integral of... Oh, and I lost a cosine. Why don't you guys say something? Cosine of x dx, because there's that cosine right there. So, when I look at this, I do have a cosine squared in here. And I have a sine of x to the n minus 2. So, what am I going to do with this? Well, I don't like having sines and cosines together. So we just used this relationship recently. Cosine squared, and how can we change that over to sines? Let's use the Pythagorean identity. This is the integral of the sine to the nth power. This is negative cosine of x sine to the n minus 1 of x plus n minus 1 times 1 minus sine squared sine to the n minus 2. Now what happens if I distribute this into my set of parentheses? Obviously when I distribute to the 1 it's the sine of x to the n minus 2 power. But then when I distribute it to this term, it works out quite nicely. Because I have sine to the n minus 2, and I'm multiplying it by sine to the second, and we know when we multiply, what do we do with exponents? We add them. Okay, so when we add those together, we have n minus 2 of them there, plus 2 more, we're back to sine to the nth. And I like that because what's on the other side of the equal sign? A sine to the nth. So, we're going to work on that. I told you this was going to be our last video. We just don't have enough time to finish. I think I'm going to need about another 4 minutes. So I apologize for that. Just go to the next video and we'll wrap up this proof of a reduction formula. We'll look at how quickly we can use this to find a couple other integrals.